Okay, welcome back. Today we are going to be talking about a very kind of interesting part of the forces unit, which is studying elevators and how they work. So, in order to study an elevator, the best and how they work and the forces involved, the best tool to use is actually a common bathroom scale. And you should either have done this lab at this point or you're just about to do this lab, so you'll see what we are looking at in person. Okay. Now, the thing about a common bathroom scale is we use it to measure our weight, right? You step on the scale, you want to see how much you weigh. So the idea is a lot of people think that a bathroom scale measures your weight, okay? How much the earth pulls down on you and how much you pull on the earth. Now, in a normal circumstance, that's more or less true, but that's not always true. And what we're going to see in this lab and in this video that you're about to watch is that a scale cannot possibly measure just your weight. Okay, it's actually measuring something else that is equal to your weight in most cases where you would want a bathroom scale. So I'm going to show you this video. This is something I found on YouTube. It's pretty good data. All it is it's just it's footage of a bathroom scale as a man is standing on it and as he's in an elevator. So I'm going to turn this so we can look at the video. And we are cutting in about 40 seconds into the video. This is right at the beginning of the video. This is the guy's about to go from the ground floor upwards. And so we're going to take a look at what the scale says, or what happens to the scale. Okay, so he's going from the ground floor up. Okay, now look where the reading is. Okay, see what happens. Now to me, it looked like the reading went up momentarily a little bit and then back down to what it started at, and now it just went down, and now it's back to its normal level. And we can see that that was where where he got off of the elevator, or where the doors opened. Okay, so what we're seeing right here is that the elevator, we watched one whole trip. At the very beginning, the elevator was just starting to go up, and then it went back, and then it stopped. Okay, now we're going to look at the downwards trip, and we got to skip forward a little bit, so bear with me. Okay. All right, so this is the downwards trip. When it starts going down, we see that the reading on the scale goes down momentarily, goes back to normal, and then let's see what happens when the elevator comes to a stop. The reading goes up on the scale, and we see that he is back on the ground floor. Okay, so let's talk about what just happened. Okay. So on the way up, in the first part of the video, what happens? As elevator starts going up, the scale reading increases, then returns to normal. And if you need to see that again, you can just go back and rewind the video, and I'm sure you can see that again. Returns to normal. And by the way, if you want to find this video for yourself on YouTube, it's just elevator bathroom scale. You can search it and watch for yourself. Returns to normal. That's not all that happened though. Just before stopping, the reading went down, and then returns to normal. Okay? On the way down, it was kind of the reverse of that. So on the way down, the reading goes down, returns to normal. And we should note that it was normal for the majority of the trip. It seemed to only be different at the very beginning and very end. Returns to normal, goes up, and that just before it stops, and then returns to normal. Now, why does this matter? Why are we spending all this time talking about this? We're trying to figure out what a scale actually tells you. Okay, so let's think about the forces that are acting on a bathroom scale. Or actually, let's think about the forces that are acting on you when you're standing on a bathroom scale in an elevator. Okay, what is the bathroom scale really measuring? Well, we have the force of gravity acting downwards on you, and we have a normal force upwards from the scale. Okay? Here's our axis. I forgot that part. Now, remember, weight, or the force of gravity, is just the force that the Earth exerts on an object and the force that that object exerts on the Earth. That shouldn't change depending on if you're in an elevator or not, if you're moving up and down in an elevator. We know the equation for weight. We know the equation for the force of gravity. It's simply the mass times the acceleration due to gravity. Your mass is how much matter you have in your body. Acceleration due to gravity is a constant 9.81 meters per second squared for objects on Earth. Okay, it's a constant. It's not saying you're accelerating at that rate. It's just a constant that is helpful in determining the force of gravity. So your weight, your mass, the amount of matter you have doesn't change if you go on an elevator. The acceleration due to gravity doesn't change. Fg shouldn't be changing regardless if you're on an elevator or not. Yet we call that weight, and yet we say that that is what the scale tells us. That doesn't really make sense. If it really was your weight, how much Earth is pulling on you, why would that change if you're on an elevator? It shouldn't, okay? It shouldn't. So what we do instead is we must realize that since the force of gravity does not change in this situation, what about the normal force? Because the scale is telling you some sort of force, okay? Could the normal force change? Could the amount that the scale presses on you change? Absolutely. You can change how much the scale presses on you or how much you press on the scale. Absolutely. So the idea here is that it must be Fn that changes, and it must be the normal force that is displayed on the scale. So scales do not actually tell you your weight necessarily, the force of gravity acting on you. They actually tell you the normal force, the force pressing up on you from the scale. Now that might be confusing. You've always used a bathroom scale to measure your weight. What we're going to see is why in most cases, in most non-physics cases, or non-physics classroom cases, that distinction doesn't really matter. Okay, let's imagine we have a man with a mass of 60 kilograms. Before he gets on an elevator, he's just standing out in the hallway, he weighs himself, he steps on the scale. What does the scale read? Well, in that case, let's just go with me for a second. Let's figure out the force of gravity on him. We can do that because we know the force of gravity is equal to the mass times the acceleration due to gravity. We have his mass, and we know what little g is, 9.81 meters per second squared. So we simply do 60 kilograms times 9.81 meters per second squared, and we find, let's see here, 60 times 9.81, we get a weight, or force of gravity, same thing, of 588.6 newtons. Okay? Now, I'm telling you that's what the scale will read. That's his weight. That's how we would determine his weight. What does the normal force acting on him? Well, I'm trying to find Fn, and in order to do that, I don't know an equation for Fn off the top of my head. There's nothing in the reference tables that has Fn equals and then a whole bunch of stuff. What I need to do is I need to, in this case, draw a free body diagram, write a net force equation, and see if I can use that to solve for the normal force. So our object is man. Here's our axis. We'll do our standard x and y. There's a force of gravity acting down on the man, which we just calculated, and there's also a normal force acting upwards on him from the scale. The net force equation, in this case, F naught in the y direction, we know the x direction, there's no forces, so 0 newtons, is Fn minus Fg equals m times the acceleration in the y direction. Now, he's not on the elevator. He's just standing out in the hallway next to the elevator. If that's the case, is he accelerating up or down? No. I know that the acceleration is 0, and if I add Fg to both sides, since this term is 0, I'm adding Fg to 0, I get Fn equals Fg. Well, guess what? I just calculated what Fg is. The normal force on this guy must be 588.6 newtons. So, under normal circumstances, when you are in your bathroom and you're stepping on the scale, what you are seeing is the normal force, okay? The normal force acting on you from the scale. But that normal force must be equal to your weight, to the force of gravity acting on you, because you're not accelerating. The whole thing with getting in an elevator and starting to move upwards is that's an acceleration. That changes what the normal force acting on you is, so the scale reading changes. But in normal circumstances, what's going to happen to you is you are not accelerating, and therefore your weight is equal to the normal force acting on you from the scale. Okay, that's why we say that a scale measures weight, because in every non-physics classroom example that you can think of, it does. But in this case, we need to make the distinction that a scale doesn't actually measure your weight, it measures the normal force acting on you. It just so happens that in most circumstances, those two things happen to be equal to each other. Let's keep going. The man gets on an upward bound elevator and steps back onto the scale. Just after the elevator starts to move up, the reading jumps to 615 newtons. What does this indicate? We'll take a look at our net force equation. If the normal force is now not the same as the guy's weight, remember, the weight can't change unless the mass changes, and we're not adding more mass to this guy. The normal force is now not the same as the weight. That means that, well, first of all, before, when we had an acceleration of 0, guess what that means about the net force? It meant that our net force was 0. If Fn and Fg were the same, then this minus this must be, and they're equal numbers, then this minus this must be 0, the net force is 0. Now, if these are not equal numbers, the net force can't be 0, and therefore the acceleration can't be 0. So, if Fn goes up, Fnet is no longer 0 newtons, and the acceleration in the y direction is no longer 0 meters per second squared. Matter of fact, we can calculate the acceleration. How am I going to do that? Well, I already know what the man's weight is, the force of gravity on him, 588.6 newtons. I know the normal force, the reading on the scale. Remember, reading on the scale, what the number of the scale tells you is the normal force. You've got to remember that, okay? It is not the weight. It's not the weight. It's the normal force. So the reading on the scale is now 615 newtons, and I know the guy's mass. I'm just going to use this part of the net force equation, Fn minus Fg equals may. The normal force is 615 newtons minus 588.6 newtons equals 60 kilograms times the acceleration. The acceleration of this man as he is accelerating when the scale is telling us that 615 newtons is the normal force is the following. 615 minus 588.6 is 26.4. I divide by 60 to get AY by itself, and I get 0.44 meters per second squared. That's literally how fast the rate at which the elevator is accelerating. Okay? We got that by doing a forces analysis. We didn't get that by measuring velocities and times and all that stuff. We got that by doing a net force analysis, and that's very interesting. We found this acceleration. Now we could actually use this acceleration to find velocities and times and distances and all that stuff. But we're not going to get that far into it right now. After a while, the reading goes back down to its normal reading. What does this indicate? The normal reading is what it was before, when the guy was outside the elevator. That was when the Fn was 588.6 newtons. So, if it goes back to normal, that just means that these two are the same again. Remember, the weight doesn't change. Fn equals Fg again. So, that means that the net force in the y direction is 0 newtons again, and AY is also 0 meters per second squared again. Now, what does that indicate? Okay, if you've done the elevator lab, you know that the reading goes back down once you're moving at a constant velocity. And that makes sense because the acceleration is 0. This is the middle of the trip. This is when your velocity is constant. You're no longer accelerating. An elevator, if you're going up, it is at rest, and then it has to accelerate to get up to its moving speed. Once it does that, that's when the reading drops back down. The reading is higher when it's accelerating, and it's normal when the elevator is in the middle of its trip as it's going up, okay, at a constant velocity. Just before the elevator stops, the reading dips down to 560 newtons. What does this indicate? Well, if we look again at our net force equation, 560 newtons would be the Fn, and then Fg is still its 588.6 newtons. So now we see that Fn is less than Fg. Let's make a prediction about this. We know that there's going to be a net force because these aren't equal. But if Fn is less than Fg, then that means we're going to get a negative number. The net force is negative. And if the net force is negative, that's also going to mean that the acceleration is negative. If you don't believe me, let's prove it. Okay, what is this man's acceleration? So we just said, again, we're going to calculate the acceleration based on the net force equation. So I'm going to do Fn minus Fg equals ma y. And again, remember, this is just before stopping. That's the key here. The normal force is 560 newtons, the force pressing upward from the scale on the man. The man's weight is 588.6 newtons, and his mass is still 60 kilograms. We're solving for AY. 560 minus 588.6, negative 28.6 divided by 60. I get an acceleration of negative 0.477 meters per second squared. What does that negative mean? Remember, we assigned up to be the positive direction. This simply means that the elevator is accelerating downward. But wait a second, it's moving upward. If it's moving upward and accelerating downward, that means the elevator is slowing down. And think about it, this is right before the elevator comes to a stop. Doesn't it have to slow down? It was moving and it's coming to rest. Okay? It must be slowing down at the top. So this all makes sense. Let's look at one more example with someone in a downward moving elevator. A 50-kilogram woman rides a downward moving elevator. Just after starting to move down, her acceleration is negative 0.45 meters per second squared as the elevator gets up to its normal speed. As the elevator stops, her acceleration is 0.5 meters per second squared. We're going to determine a few things. Her weight, her apparent weight, which is another name for the normal force. I'm going to mark that down, okay, Fn. Her apparent weight as she starts to move down, her apparent weight in the middle of the trip, and her apparent weight as she comes to a stop. That's a good name for what the scale tells you, your apparent weight, okay? Because it can change. Your weight itself does not change. The earth doesn't pull on you any more strongly or less strongly just because you're in an elevator. That doesn't make sense. Your apparent weight, however, it seems to change. And that's the clue that tells you the scale does not actually tell you your weight. It tells you the normal force acting on you. Okay. Notice that this time we're given the accelerations, we're asked to find the apparent weight, the normal force. We're still going to use the same type of equation. It's just we're kind of going backwards from what we did before. All right, let's start out by finding her weight. Fg equals mg. Fg equals 50 kilograms multiplied by 9.81 meters per second squared for little g. And it turns out that Fg is equal to 490.5 newtons. So there's her weight. Now we need her apparent weight as she starts to move down. I'm solving for Fn, the apparent weight here, or the normal force. They mean the same thing. But I don't know any equations for Fn. I really should draw that free body diagram again. It's going to be the same looking free body diagram. That's the nice thing. Label, axis. We have a normal force pointing up. We have a force of gravity pointing down. Notice that I'm not scaling my diagram. I may ask you to do that at some point. Okay? So if one of the forces is bigger, you would have to draw it bigger. The net force equation is F net y equals Fn minus Fg equals may. Well, as this woman starts to move down, again, we're not looking for the normal force here, but that would be easy enough to solve for if I knew the difference between Fn and Fg, or if I knew the product of m and ay. I could calculate the normal force. That would be very easy. That's actually part of your lab. So I have Fn minus Fg equals may. I have Fn minus her weight, 490.5 newtons, equals 50 kilograms times, what's the acceleration when the person starts to move down? Negative 0.45 meters per second squared. So I do 50 times 0.45 negative 22.5. And to get Fn by itself, I'm going to add over the 490.5. notice that that product was negative, so that when I add over 490.5, the normal force on this woman is only 468 newtons. So notice that when they start to move down, okay, when the person starts moving down, the normal force is actually less than it was normally when they were at rest. In the middle of the trip, the normal force should be the same, or actually we shouldn't say that. We should say the acceleration of the elevator is 0. So in the middle, we have Fn minus Fg equals may. In the middle, we know that the elevator is moving at a constant velocity. Okay, it's normal speed. That means the acceleration is 0. It doesn't mean it's not moving, it's just not accelerating. The velocity is not changing, the speed's not changing. Which means Fn equals Fg, we just add the Fg over to the other side. Therefore, the Fn, the normal force, the apparent weight, must be 490.5 newtons. So again, in the middle of the trip, everything is back to normal. And finally, at the end of the trip, when they are stopping at the bottom, let's see what happens here. Now we have a positive acceleration. We multiply 50 and 0.5, and then we add over 490.5, and we see that the normal force is bigger than normal, 515.5 newtons. We're going to stop there for this video, just so I don't risk getting cut off. In the next video, we're going to categorize what has happened here, and we're going to come up with a chart that tells you what should happen to the acceleration and what should happen to the normal force, or apparent weight, as an elevator either goes up or goes down during the different phases of motion. And we're even going to throw in how do you feel. And then we'll move on to some examples.